NEC 702.5 addresses the sizing and installation of optional standby systems, which are not required but are installed for emergency backup power. NEC 702.5 allows the user to select the loads connected to the optional standby system. This suggests that the user has the discretion to determine the size of the generator based on their expected load requirements. However, the electrical engineer's concern about sizing the generator according to the maximum possible load and the switch is valid in certain situations. For example, in a house with a 200 amp main feeder, installing a 15 kilowatt generator that is rated less than the main breaker could result in the generator failing to provide adequate power in the event of a high load situation. It is true that overcurrent protection devices and the generator will trip if the load exceeds the generator's capacity. However, this could lead to a loss of power for critical appliances or equipment connected to the generator. It is essential to ensure that the generator is sized appropriately to handle the expected load while providing sufficient overload protection. Transfer switches with generator side ratings less than the primary supply side ratings are used to prevent overloading the generator. This allows the user to connect a smaller generator to a larger distribution system while ensuring that the generator does not exceed its rated capacity. While the NEC allows the user to select the loads connected to an optional standby system, it is advisable to consider the maximum possible load in the connected equipment. Sizing the generator appropriately, with sufficient overload protection, will ensure reliable backup power while minimizing the risk of generator failure due to overloading. It is recommended to consult with both the electrical engineer and the homeowner to determine the appropriate generator size based on the following factors. Firstly, expected load requirements. Secondly, maximum possible load and the connected equipment. Thirdly, electrical code requirements. And fourthly, safety concerns. Let's delve into a more detailed explanation of each of these points, expanding on the considerations and calculations involved. When assessing the expected load requirements, it's crucial to have a comprehensive understanding of what the homeowner intends to power during an outage. This isn't just about the bare essentials, it's about comfort, safety, and the ability to maintain a reasonable quality of life. Here's a breakdown of how to approach this assessment. Firstly, create an itemized list. Work with the homeowner to create a detailed list of all the appliances and equipment they want to be able to run on the generator. This should include everything from refrigerators and freezers to lighting, heating or cooling systems, medical equipment, and entertainment devices. Secondly, determine the wattage of each item. For each item on the list, find its wattage rating. This is typically found on a sticker on the appliance or in the owner's manual. If the wattage isn't listed, you can calculate it by multiplying the voltage by the amperage. Voltage amps equals watts. Thirdly, distinguish between starting and running wattage. Some appliances, particularly those with motors like refrigerators and air conditioners, require more power to start than they do to run continuously. The starting wattage can be significantly higher, sometimes 2 or 3 times the running wattage. Make sure to note both for each appliance. Fourthly, consider simultaneous usage. Realistically assess which appliances and equipment are likely to be used at the same time. It's unlikely that everything will be running simultaneously, so you can avoid oversizing the generator by considering realistic usage patterns. For example, the microwave and the air conditioner might not be used at the same time. Fifthly, calculate the total running wattage. Add up the running wattages of all the appliances and equipment that are likely to be running simultaneously. This will give you an estimate of the generator's required running wattage. Sixthly, calculate the total starting wattage. Identify the appliance with the highest starting wattage. Add this to the total running wattage you calculated earlier. This will give you an estimate of the generator's required starting wattage. When evaluating the maximum possible load on the connected equipment, it's important to consider scenarios where the homeowner might inadvertently or intentionally overload the generator. This is where the electrical engineer's concern about sizing the generator to the maximum possible load comes into play. Here's how to approach this aspect. Firstly, identify all potential loads. Make a comprehensive list of every electrical device in the house, even those not typically used during an outage. This includes lights, appliances, outlets, and any other electrical load. Secondly, determine the maximum wattage for each load. For each item on the list, determine its maximum possible wattage. This might be higher than the typical running wattage, especially for devices with variable power settings. Thirdly, consider all loads running simultaneously. Imagine a scenario where every light is turned on, every appliance is running at its maximum setting, and every outlet is being used to power some device. This is the maximum possible load scenario. Fourthly, calculate the total maximum wattage. Add up the maximum wattages of all the devices on the list. This will give you the total maximum wattage that the generator might have to handle. Fifthly, compare with the generator's capacity. Compare the total maximum wattage with the generator's rated capacity. If the total maximum wattage exceeds the generator's capacity, you need to either increase the generator size or implement load shedding measures to prevent overloading. Exploring electrical code requirements involves ensuring that the generator installation complies with all applicable electrical codes and regulations. This is crucial for safety and to avoid potential legal issues. Here is a breakdown of the key considerations. Firstly, reference NEC 702.5. As discussed earlier, NEC 702.5 provides guidance on sizing and installing optional standby systems. Review this section carefully to ensure compliance. Secondly, check local codes and regulations. Local electrical codes and regulations may have additional requirements or restrictions that go beyond the NEC. Check with the local authorities to ensure compliance. Thirdly, consider permitting and inspection requirements. Most jurisdictions require a permit for generator installations. Obtain the necessary permits and schedule inspections to ensure that the installation is done safely and according to code. Fourthly, ensure proper wiring and grounding. A generator must be properly wired and grounded to prevent electrical hazards. Use appropriately sized wiring and grounding conductors, and follow all applicable codes and regulations. Fifthly, install a properly rated transfer switch. A transfer switch is required to safely switch between the utility power and the generator power. Choose a transfer switch that is rated for the generator's output and that complies with all applicable codes and regulations. Finally, address safety concerns. Safety is paramount when installing a backup generator. The generator must be installed and operated safely to prevent electrical hazards, fire hazards, and carbon monoxide poisoning. Here's how to approach safety considerations. Firstly, install carbon monoxide detectors. Install carbon monoxide detectors in the home to alert occupants of dangerous levels of carbon monoxide. Secondly, ensure proper ventilation. The generator must be properly ventilated to prevent the buildup of carbon monoxide. Follow the manufacturer's instructions for ventilation requirements. Thirdly, use a properly rated extension cord. If using an extension cord to connect the generator to appliances, use a heavy-duty extension cord that is rated for the generator's output. Fourthly, keep the generator dry. Protect the generator from rain and snow to prevent electrical hazards. Fifthly, follow the manufacturer's instructions. Follow the manufacturer's instructions for installation, operation, and maintenance of the generator. Sizing a generator involves the NEC load considerations and safety. A balance between user needs, code compliance, and safety is critical for the backup system. Consider a load calculation. Here's a breakdown for the load calculation and NEC articles to be considered. Firstly, service entrance size. Determine the existing service entrance size to establish a baseline for the dwelling's electrical capacity. This is often 200 amps for a typical single-family home, but could be lower or higher. Secondly, NEC Article 220, branch circuit, feeder and service calculations. This article provides the comprehensive methodology for calculating electrical loads and residential occupancies. It guides the process of determining the minimum size of conductors and overcurrent protection for various circuits, feeders, and services. Thirdly, general lighting load. Calculate the general lighting load based on the dwelling square footage per NEC 220.12. This calculation ensures adequate capacity for general illumination throughout the house. Fourthly, small appliance and laundry circuits add the mandatory small appliance branch circuits amps and the laundry circuit amps as required by NEC 702.5. These circuits are essential for powering common household appliances and laundry equipment. Fifthly, appliance loads calculate the loads for specific appliances such as ranges, ovens, dryers, water heaters, air conditioners, and heat pumps based on the nameplate ratings in accordance with NEC 220.53, 220.54, 220.55, 220.56, 220.57. These calculations ensure that the service has enough capacity to handle the demands of these appliances. Sixthly, heating and cooling loads determine the larger of the heating or cooling load as per NEC 220.60. This step prevents oversizing the service by accounting for the fact that heating and cooling systems are not typically used simultaneously. Seventhly, optional calculations explore the optional calculation method in NEC Article 220 Part 4, which can often result in a lower calculated load, particularly for dwellings with diverse loads. These optional calculations may be applicable based on specific circumstances. Eighthly, demand factors. Apply demand factors to various loads as permitted by NEC Article 220 to account for the likelihood that not all loads will be operating at their maximum simultaneously. Demand factors reduce the calculated load, leading to a more realistic assessment of the service requirements. Ninthly, total calculated load. Sum up all the calculated loads, taking into account demand factors and any applicable optional calculations to arrive at the total calculated load for the dwelling. This represents the maximum amount of power the service is expected to deliver under normal operating conditions. Tenthly, generator sizing. Use the total calculated load as a basis for determining the appropriate size of the backup generator. The generator should have sufficient capacity to supply the calculated load without overloading. Now let's consider load management strategies and technologies which are vital in generator sizing. Firstly, load shedding systems. Implement load shedding systems to automatically disconnect non-essential loads during generator operation to prevent overloading. These systems prioritize essential circuits and shed lower priority loads. Secondly, smart home integration. Integrate smart home technology to monitor and control electrical loads, allowing for real-time adjustments to optimize generator performance and prevent overloads. Smart home systems can provide valuable data and control capabilities. Thirdly, energy-efficient appliances. Encourage the use of energy-efficient appliances to reduce overall electrical demand and minimize the generator size required. Energy-efficient appliances consume less power, reducing the burden on the generator. Fourthly, time of use scheduling. Schedule the operation of certain appliances, such as pool pumps or electric vehicle chargers, during off-peak hours to minimize the generator load during critical periods. Time of use scheduling helps distribute the load more evenly. Fifthly, surge protection. Install surge protection devices to protect sensitive electronic equipment from voltage spikes and surges that can occur during generator operation. Surge protection safeguards valuable electronics. Sixthly, power monitoring systems. Utilize power monitoring systems to track energy consumption and identify opportunities for load reduction and optimization. Power monitoring systems provide insights into energy usage patterns. Lastly, professional consultation. Consult with qualified electrical engineers and contractors to assess the dwelling's electrical needs and determine the optimal generator size and configuration, ensuring compliance with NEC requirements and local codes. Professional expertise is invaluable in making informed decisions. The NEC provides a framework for electrical installations, and understanding its requirements is essential for safety and compliance. NEC 702.5 is particularly relevant when sizing backup generators for optional standby systems. This section allows the user to select the loads connected to the system, but it's crucial to consider the maximum possible load that could be placed on the generator. If the generator is not sized appropriately, it could lead to overloading, which can damage the generator and leave the homeowner without power when they need it most. When sizing a generator, the first step is to determine the loads that the homeowner wants to be able to run during an outage. This includes essential loads such as refrigerators, freezers, and medical equipment, as well as non-essential loads such as lights, televisions, and air conditioners. Once the loads have been identified, the next step is to calculate the total wattage of these loads. This can be done by looking at the nameplate rating of each appliance or by using a clamp or ammeter to measure the current draw of each appliance. After the total wattage has been calculated, the next step is to apply demand factors. Demand factors are used to account for the fact that not all loads will be running at the same time. For example, a homeowner may not be using their air conditioner and their electric stove at the same time. The NEC provides demand factors for various types of loads, which can be used to reduce the total calculated load. Once the demand factors have been applied, the next step is to determine the minimum size of the generator. The generator should be sized to handle the total calculated load, plus a safety margin of 10 to 20%. This safety margin will help to ensure that the generator is not overloaded, even if the homeowner turns on more appliances than expected. In addition to sizing the generator, it's also important to consider the transfer switch. A transfer switch is used to switch between the utility power and the generator power. The transfer switch should be sized to handle the full load of the generator. It's also important to make sure that the transfer switch is properly installed and grounded. Finally, it's important to have the generator installation inspected by a qualified electrical inspector. The inspector will make sure that the generator is properly installed and that it meets all applicable codes and regulations. Sizing a generator can be a complex process, but it's important to take the time to do it right. A properly sized generator will provide reliable backup power during an outage, while an undersized generator could be damaged or fail to provide enough power. By following the steps outlined above, homeowners can ensure that they have a generator that is sized appropriately for their needs. Now let's discuss generator maintenance best practices, which are very important in the lifespan of the unit. Firstly, regular inspections. Perform regular visual inspections of the generator, checking for any signs of damage, leaks, or corrosion. Regular inspections can identify potential issues early on. Secondly, oil changes. Change the generator's oil according to the manufacturer's recommendations, typically every 50 to 200 hours of operation. Regular oil changes ensure proper engine lubrication. Thirdly, air filter cleaning or replacement. Clean or replace the air filter regularly to ensure proper airflow to the engine. A clean air filter helps the engine run efficiently. Fourthly, spark plug maintenance. Inspect and replace the spark plugs as needed to maintain proper ignition. New spark plugs ensure reliable starting. Fifthly, fuel system maintenance. Drain and flush the fuel tank periodically to remove any sediment or contaminants. Clean fuel is essential for smooth operation. Sixthly, battery maintenance. Check the battery terminals for corrosion and clean them as needed. Ensure the battery is properly charged to provide reliable starting power. Seventhly, load testing. Perform load tests periodically to ensure the generator can handle its rated load. Load testing verifies the generator's capacity. Lastly, professional servicing. Schedule professional servicing and maintenance at least once a year to ensure the generator is in optimal condition. Professional servicing can identify and address potential problems. In summary, understanding and implementing these strategies ensures a safe, compliant, and reliable backup power system that meets the homeowner's specific needs. It's a collaborative process requiring input from both the homeowner and qualified professionals.